So for today, we will continue with read mapping topic. We will have very recent work from our Safari research group at ETH Zurich called GenStore. And we have Nika. She's a PhD student with us at Safari group. She will be presenting about this work, which was published in S+ this year. So yeah, without further ado, Nika, go ahead. And guys on YouTube, feel free to ask questions in the chat box anytime. We can take them and try to answer. Go ahead, Nika.
Okay, cool. Thank you very much, Mohammed, for the introduction. So I assume that then the screen and everything is fine with the sharing. So yeah, welcome everyone to this lecture, lecture 7 in PNS mobile genomics class, which we will talk about GenStore. GenStore is a high performance and storage processing system for genome sequence analysis. And as Mohammed mentioned, this work was originally presented in S+ 2022. Genome sequence analysis, as you by now know, is critical for many applications such as personalized medicine, outbreak tracing, and evolutionary studies. Genome sequencing machines extract the smaller fragments of the original DNA sequence, known as reads. And as you know, also read mapping is the first key step in many genome sequence analysis applications that aligns reads to potential matching locations in the reference genome. And for each matching location, using the alignment step, it finds the degree of similarity or the alignment score between the reads and the reference genome. Calculating the alignment score requires computationally expensive approximate string matching, or ESM, to account for differences between the reads and the reference genome, which may occur due to sequencing errors and also genetic variation. Read mapping performs alignment on large genomic data sets containing millions of reads. Therefore, read mapping is both computationally expensive and incurs high data movement overhead from storage. There has been significant effort into improving read mapping performance through efficient heuristics, hardware accelerators, and various filters that pruned reads that would not require these expensive computation. And by now in the class, you've learned about many of these approaches. While these approaches effectively reduce the computation overhead in read mapping, none of them alleviate data movement overhead whose impact from storage, whose impact becomes even larger when the computation overhead gets alleviated. So the key idea of our work is to filter reads that do not require alignment inside the storage system so that we can fundamentally reduce the cost of data movement from storage system to the rest of the system. So example of reads that would not require this expensive computation are exactly matching reads that do not require expensive approximate string matching during the alignment because they would exactly map to the reference genome, and non-matching reads, which are basically reads that do not have any matching location in any place in the reference genome, and therefore they do not need alignments because there's no location in the reference genome to align to. However, filtering the reads in a modern SSD can be challenging because read mapping can exhibit different behavior across different read mapping workloads and different input data sets. And there is limited hardware resources in the SSD available. So by addressing these challenges, we propose GenStore, which is the first in storage processing system for genome sequence analysis, to reduce both the computation overhead of read mapping and address the data movement overhead from storage. GenStore provides high performance and energy benefits compared to state-of-the-art hardware and software baselines at low area cost. So this was a summary of my talk. Let's start with a deeper background on read mapping so that we refresh our knowledge on it, basically, since I know that we've covered the background already in the lecture. So we refresh our knowledge on read mapping and we can dive into this talk in more detail. Mapping reads to reference genome requires expensive computation on large data sets, and the search space in the reference genome can be very large. For example, the human reference genome contains more than 3 billion characters. Therefore, read mappers typically use an index structure of their reference genome to reduce the search space. This index contains unique K-length subsequences called k-mers extracted from the reference genome and the locations of each of these k-mers in the reference genome. So read mapping is a three-step process, and state-of-the-art read mappers involve several heuristics to reduce the cost of expensive computation. So let's go through these steps. In the first step, which is called seeding, the mapper determines some potential matching locations or seeds in the reference genome to which the read would basically align. So to do so, the read mapper first extracts the small k-mers from the read, looks at the location of each of these k-mers in the reference index, and in case the k-mer hits in the index, it marks the locations of these k-mers in the reference genome as seeds. To further reduce the cost of this expensive computation, the second step, which is seed filtering, for example, chaining, prunes some of these seeds in the reference genome so that we would basically do that alignment step on smaller candidate locations. And to do that, the mappers use a simpler approximation of alignment score called chaining score, which is less computationally intensive compared to the alignment. And then finally, for the remaining reads for the reads in the second step that do not have any potential matching location left, they would be ignored from the third step, they would be dropped. And for the reads that have some potential matching locations left, the third step, which is the alignment step, the computationally expensive approximate matching step, executes to determine the exact differences between the read and the reference genome. So we perform experimental studies to understand the potential of ideal in storage filter for improving read mapping performance. And to do that, we perform a case study on real-world genomic data set on various read mapping systems and the state-of-the-art SSD configurations. And by that, we make several key observations and takeaways. First, the ideal in storage filter can significantly improve performance by reducing the computation overhead and data movement overhead from storage. And second, filtering outside SSD provides lower performance benefits compared to an ideal in storage filter because it does not reduce the data movement overhead from storage. And also it must compete with read mapping for resources across the system. For example, with compute resources, memory bandwidth, and external SSD bandwidth. And also we observe that hardware accelerator reduces the computation bottleneck, which makes the IO actually a larger bottleneck in the system. So we have discussed several approaches that greatly reduce performance overhead of read mapping in the previous lectures. And actually by leveraging these advanced optimizations, we observed that since the computation overhead is becoming much smaller, it becomes even more critical to address the IO bottlenecks because the relative overhead here in the system increases. So based on these observations and motivated by these motivational studies, our goal is to design a storage filter for genome sequence analysis in a cost-effective manner. And to do that, we have three key design objectives in mind. First is to provide high performance of storage filtering by overlapping the filter process in the SSD with the read mapping of unfiltered data. So we want to send the unfiltered data meanwhile to the system that performs read mapping, meanwhile that we are performing filtering inside the SSD. And the second constraint is the second objective is to have high applicability across many different genomic read sets with different properties, such as their length and error rates and different degrees of genetic variation compared to the reference genome that you're being aligned to. And in the end, our third design objective is not to require high hardware overhead. And to this end, we propose GenStore, which is the first in-storage processing system designed for genome sequence analysis. And our key idea is to filter reads that do not require alignment inside the storage system and send the unfiltered data to the host system for further processing. However, filtering reads in a modern SSD can be challenging due to different behavior across read mapping workloads and the limited hardware resources in the SSD. We will get into these challenges in more detail. So now let's take a look at filtering opportunities based on various input data sets with different properties. So sequencing machines produce one of two kinds of reads. First are short reads that are highly accurate but are short, and long reads that are less accurate but are long. And reads that do not require the expensive alignment step and therefore are good candidates for the in-storage filtering, which we leverage in this work, are exactly matching reads that do not require expensive approximate string matching during alignment, and that frequently occurs in low with reads that have short reads that have low sequencing error rates and also have low genetic variation. The second class of reads that can be filtered simply are non-matching reads that do not have any potential matching locations and they can skip alignment. And examples of these frequently happen in high sequencing error rates, such as long reads, or with or long or short reads that have high degree of genetic variation. So by thorough analysis of mapping process of reads with different properties and different degrees of genetic variation, we designed two low-cost in-storage filters. First is GenStor EM for exactly matching reads, and GenStor NM for filtering most of non-matching reads. So let's take a closer look at GenStor EM. GenStor EM accelerates read mapping by using an efficient in-storage filter to filter reads that have at least one exactly matching location in the reference genome via only simple operations without requiring expensive alignment. However, doing so is challenging inside the storage because of large number of random accesses per read to the reference genome and its index. So if you remember, based on the background that we just discussed, for every read we extract several k-mers, and for the several k-mers we access the index and find some candidate locations in the reference genome, and we also access the reference genome. So there are like many random accesses for every read. And that is challenging in modern NAND flash-based SSDs because of two reasons. First is the poor performance of random accesses in NAND flash chips. And the second one is the limited DRAM capacity inside the SSD, which is relatively small compared to the size of data structures that need to be randomly accessed. So for example, typically for modern SSDs, we have 1 gigabyte of DRAM compared to a terabyte of storage. So the DRAM inside the SSD is very small and we can't really have efficient random accesses to NAND flash chips. So to reduce the number of accesses per each read, we introduced the concept of read-sized k-mers. Therefore, instead of extracting several k-mers per each read, we consider that a read is one k-mer. So we introduced the concept of read-sized k-mers in a sense. So therefore, instead of having several k-mers to look up to the index and reference genome several times, we would have only one lookup, one index lookup per every read. So that reduces the number of random accesses. So now with these read-sized k-mers, we have the ability to sort them because we would have only one access per every read, so we can already sort them. So then we introduce the concept of sorted read-sized k-mers to avoid random accesses to the index, because that enables us to sequentially scan the read set and the index instead of randomly accessing them. So by these two optimizations, first of all, we reduce the number of lookups and also turn the random accesses into more efficient streaming accesses. So now let's look at this key idea of GenStor EM with a simplified example in which each short read consists of 10 characters. So usually a short read can be like few hundreds, like let's say 150 or around that range. But for now, I'm just going to, for simplicity, use a read data set that each read has 10 characters. Based on that, we introduced two data structures in our work. First is a sorted read table, each entry of which stores a read and its unique ID, and a sorted k-mer index, which contains all the unique read-sized k-mers extracted from the reference genome, along with each k-mer's corresponding location in the reference genome. So if you remember when I was discussing refreshing the background of read mapping, we discussed an index with the small k-mers and the locations of them. Now we generate somehow the same type of index, but this time with much larger k-mers, again, extracted from the reference genome and with the locations of these k-mers in the reference genome. So also, each data structure is preprocessed and is sorted based alphabetically in this example, based on the read and k-mers in each table. So we sequentially scan through these data structures in 3 different ways based on the comparison result of the current read and k-mer. So first, when the current read and k-mer are identical, then we detect that, okay, the read is an exact match and can be filtered from further read mapping analysis. So by filter here, we do not mean neglect or basically throw out. It means that it will be filtered out from further read mapping analysis in the read mapper, and it does not need expensive computation. So we'll mark this read as an exact match and filter it from inside the storage. Then we go to the next element in each of these tables to to find more matching reads or non-matching reads. So here, when the read is bigger than a k-mer, alphabetically larger than a k-mer, we conclude that the k-mer does not match any read. Because since we've been sequentially scanning through it, we would already see the match if that was the case, if the k-mer would match any read. So then we go to the next element in the sorted k-mer index so that we can examine the next k-mer. And then finally, if the k-mer is alphabetically larger than the read, we conclude that the read does not match any k-mer in the index, meaning it does not match any place in the reference genome. Therefore, it's a non-matching read and needs to be sent to the full read mapping process. Whatever that system is, a software read mapper or hardware read mapper. So that will go to outside the storage to that system. And then we go to the next element in the sorted read table so that we can examine the next read. So using this technique, GenStor-EM avoids random accesses to the index and to the read data structure, to the read sets, and performs filtering using only one simple low-cost comparison operation per each read. So despite the key benefits of this sorted read-sized k-mer index, this index takes up a large space. For example, for a human index, it takes 128 gigabyte size due to the large number of unique read-sized k-mers. And also, we can't use techniques like minimizers to reduce the number of let's say entries in the table, because we really want to find the exact matches if they exist. So we can't afford any common techniques in bioinformatics to reduce the size of this table by reducing, let's say, the elements. So
Mika?
Yes?
Is there a maximum length that you can consider here for the k-mer size?
Not necessarily, because so yeah, I see your point. So the length, when it increases, comes with two drawbacks. One is that the table size increases. So if we can tolerate that, that is fine. And I will explain the next step, which is the hash function, which we replace the k-mers with them. So in order to avoid collision in those hash values, we need to also increase the length of the hash value, which comes at increased data structure size. So if that can be afforded, that is possible to scale up the size of this to larger reads. But it is very important and critical to understand the overhead and tune the hash value size accordingly to avoid collisions.
Mm-hmm.
Yeah, great question, thanks. Yeah, okay, so the size of this table increases because of the unique number of k-length subsequences. And we can't also use common techniques to reduce the size of this table, like minimizers, let's say. So then we reduce the overhead of this table by replacing the read-sized k-mers with a strong hash value of each read that can act as both the sorting criterion. Instead of alphabetic sorting, we can now sort with these hash values. And then it can be also acting as the fingerprint of each entry. So we compare the hash value of the k-mers with the hash value of reads to find matches and mismatches. So that can, therefore, the use of these strong hash values instead of the larger k-mers reduces the size of the index by 3.9 times. And this index is still larger than the baseline k-mer index used in the conventional read mappers. However, our proposal is feasible for in-storage processing because of the large capacity and high internal bandwidth of modern NAND flash-based SSDs. Basically, in a sense, we trade off the storage space and basically number of elements in the table so that we fit within these the constraints of the architecture that we're designing this accelerator for. So it is very critical to avoid random accesses, and sequential accesses are much more efficient. So therefore, we trade off to increase the size of the data structure based on these constraints. So now I show the overall operation flow of GenStore EM with SR table and SK index in the NAND flash memory, which are distributed across different channels and dies planes inside the SSD, so that since this data is evenly distributed, we can leverage the full internal bandwidth of the SSD, which is usually much higher than the external bandwidth of the SSD. We also have the comparator logic as a small accelerator implemented inside located on the SSD controller. So GenStore EM consists of two steps. Step one reads the two data structures from the NAND flash chips in the SSD's internal DRAM in a batched manner and puts it in the DRAM inside the SSD. And since we read sequentially, we can just read in small batches. And we don't need to have the whole table or whole index in DRAM. Therefore, only a few hundred megabytes of DRAM is enough to enable us to keep the full throughput of basically leveraging the internal bandwidth of the SSD, actually. So then step two performs exact match filtering within each read batch using simple comparator logic. And step 1 and 2 are performed in a pipelined manner. And that actually enables us that during filtering, send the unfiltered reads to the host system for full analysis. So meanwhile, that these inside the SSD, we are working on the filtering, the read mapping can in parallel basically happen in the host system. And the reads that are filtered do not waste the external bandwidth of the SSD or the main memory bandwidth of the system, the host system. So that would be basically the overall flow of GenStore EM. So now let's take a closer look at GenStore NM. GenStore NM, which was used for filtering most of the non-matching reads using chaining, tries to basically filter these most of these non-matching reads that would not align to any subsequences in the reference genome. By leveraging chaining. So recall that in the high-level three-step process that we talked about, chaining filter calculates the similarity score for each read, which is called the chaining score, and filters the reads that in the end would not have any potential matching locations left. So calculating the chaining score in SSD can be challenging because finding the best chaining score requires performing many iterations of a dynamic programming algorithm for all seeds in a read. And that can be particularly challenging for long reads since they have large number of k-mers per read. So if we want to actually, for a long read, perform this at high throughput so that we can also leverage the full internal bandwidth and full throughput of the SSD, we would need to trade off large area by increasing the parallelism of this accelerator, the chaining filter. And that would incur high area size for logic and the buffer space that we would need. So that would be inefficient for long reads that can have extremely large number of seeds. So to reduce the cost of chaining, Genstar NM uses a lightweight chaining filter that selectively performs chaining only on reads with a small number of seeds and directly sends the reads that require more complex chaining to the host system. This idea is based on our observation from analyzing a wide range of real-world genomic datasets. And this figure shows the alignment probability of a read in a long-read dataset to subsequences in the reference genome as a function of number of seeds per read. We observed that reads with sufficiently large number of seeds are very likely to align to subsequences in the reference genome. And such reads can be directly sent to the CPU or an accelerator for full read mapping, bypassing the in-storage filter. Basically, in a nutshell, there is no point in investing, having a bulky accelerator to work with reads that have many seeds, because these reads in all likelihood would not be filtered. So we conclude that the selective lightweight chaining approach can filter many non-aligning reads without costly hardware resources in the SSD. So for more details on Genstar NM design, please refer to our paper. Okay, so now I will go into our results. So we evaluate the following systems. For base, we use the state-of-the-art software and hardware read mappers for short and long reads. So for software, we use Minimap2, and for hardware, we use GenCache and Darwin. And the point here to emphasize actually is that the faster the read mapping becomes actually by optimizing it more or using it even newer accelerators or combining different techniques to optimize the read mapping process, actually the benefits of Genstar would increase because, as I discussed, relatively the impact of I/O overhead becomes higher. So we compare these systems with GS, which is base integrated with Genstar. So that means that we compare, let's say, a hardware mapper with a hardware mapper integrated with Genstar, because Genstar can be combined with different software or hardware systems since it orthogonally is running inside the SSD. So that is basically the comparison point. And we also try to analyze various state-of-the-art SSD configurations. For example, SSD-L is the state-of-the-art SATA SSD, and SSD-M, which is a PCIe Gen 3, and SSD-H, which is state-of-the-art PCIe Gen 4 SSD. So as you see, these SSDs gradually, as you see, they're providing higher bandwidth. However, it is important to note that it is still important to analyze Genstar or like keep in mind the low-end SSDs like SSD-L, because in very large scale systems, the number of PCIe slots are usually relatively limited, and they are shared among many other systems. For example, they can be connected to a GPU or an accelerator connected to the those PCIe slots. So relatively, we have a smaller number of PCIe slots in the system available for expanding the storage infrastructure compared to SATA. And it is also usually a lot more cost effective to use SATA interface. So that is why in our work, we try to cover all these circumstances, because that would gain us a deeper understanding on how Genstar would perform in high-end SSD and in larger scale systems that they need to use more low-end SSDs. So we analyzed the benefit of GenStor EM for a 22 gigabyte short read set where 80% of reads exactly match to some subsequences in the reference genome and can be filtered. We show the benefit of GenStor on software and hardware read mappers. And GenStor provides 2.1 to 2.5 times speed up compared to the software baseline, and 1.5 times to 3.3 times speed up compared to the hardware baseline. And on average provides 3.9 times energy reduction. So now we analyze the benefits of GenStor NM for a 12 gigabyte long read set with high degree of genetic variation compared to the reference genome, and where a large fraction of reads do not match any subsequences in the reference. And we show the benefits of it on software and hardware mappers. So GenStor provides up to 27.9 times the speed up compared to the software baseline, and up to 19.2 times the speed up compared to the hardware baseline, and on average 27.2 times energy reduction on this input data set, which has very high genetic variation. So we find the area and power values of GenStor by synthesizing GenStor EM and NM using 65 nanometer technology node, and find that for an 8-channel SSD, the area of GenStor is 0.2 millimeters square, and power is 26.6 watts. And by scaling the area to lower technology nodes to have a fair comparison to some common systems, we observed that the area overhead of GenStor is 0.006% of an Intel processor and less than 9.5 times of the 3 ARM processors in a SATA SSD controller. And in an SSD controller, we have also many different accelerators for different, let's say, functionalities, or we have ECC units. So this, in the end, has larger area, but even compared to those 3 small ARM cores inside the controller, that takes only 9.5%. So let me briefly talk about some other results that are included in the paper before concluding this talk. So these include the following. We analyze the effect of read set features on performance. So we scale up the data sizes to up to 440 gigabytes. And the filter ratio, which is the ratio of reads that will be filtered. So as you see, we discussed some examples here, but we discussed a wider range of read filtering ratios for different types of reads and different read mapping use cases. And we also show performance benefit of implementation of GenStor outside the SSD, because as we discussed, GenStor provides some key benefits. For example, it reduces the number of accesses to an index, or it sequentializes the otherwise random accesses. So, however, it also comes at a cost of larger data size. So we analyzed the benefits of these optimizations, assuming GenStor is an accelerator outside the SSD. And we observed that in some cases, it provides performance benefit due to more efficient streaming accesses, but it provides significantly lower benefit compared to GenStor because it does not alleviate the cost of data movement from storage, and also due to larger data sizes. For some cases that the read mapping is super fast, these larger data sizes might incur some overhead, but these designs are tailored for inside the SSD that would enable us to stream through these large data sizes very efficiently. So then we conclude that in high performance read mapping systems, it becomes increasingly critical to actually devise a storage solution to benefit from filtering process. And we also provide more detailed characterization of non-magic reads across different read mapping use cases and species based on real genomic data sets. So let me now conclude by giving the summary of this talk. So there has been significant effort into improving read mapping performance through efficient heuristics, hardware accelerators, and accurate filters. And the problem is that while these approaches address the computation overhead, none of them alleviate data movement overhead from storage. And our goal is to improve the performance of genome sequence analysis by efficiently reducing unnecessary data movement from storage system. And our idea is to filter reads that do not require the expensive alignment computation in the storage system to fundamentally reduce the data movement overhead. And we need to tackle two challenges, which were read mapping workloads exhibiting different behavior for different genomic data sets and the limited available hardware resources on the storage system. And by addressing these, we propose GenStor, the first storage processing system designed for genome sequence analysis to reduce both computation and data movement overhead. And GenStor provides a significant speed up and energy reduction for hardware and software read mappers at low area cost. So yeah, that will conclude my talk. And thank you very much for listening.
That was great, Nika.
Thank you very much.
Do we have any questions from the audience? I see one wish on YouTube. They want the talk in Turkish, but unfortunately we are at ETH Zurich, Switzerland, where the medium of teaching is English. But hopefully you can use the service from YouTube to, I don't know, transcribe the talk to the language you prefer. So I have one question. If someone wants to practically use GenStor, how he should deal with it?
What aspects of practical use are you referring to?
Can he have some source code downloaded, run it? Can he purchase this kind of GenStor enabled SSD and try to use it directly in his machine, her machine? Okay,
that's great. Good point. So for software implementation and HDL implementation of it, we have already open source in Safari GitHub repo. But how would one practically use it? So for software that is explained in the repo how to use it, but for hardware, there are two ways I can see. So there are some systems that already try to integrate some FPGAs densely integrated within the SSD controller that would enable near storage processing. So it is possible to implement the HDL code inside the SSD and also handle the control flow from the, basically whatever that FPGA is using to interface with the NAND flash chips. So that is one way. And the other way is to have SSD controllers in the future that would fabricate simple filters for genomic, let's say, data centers or genomic systems that would need such optimizations. But the last solution, of course, is not practical right now. I think the other two solutions might be more useful for now.
Yeah, that's very nice. And where do you think the great benefits should come from, whether using GenStor alone or integrating it with existing accelerators, for example?
Yeah, so integration of GenStor with both hardware and software systems provides large benefits. But the importance of it, I believe, will become even more, or like it will become more beneficial when the read mapping process would become faster, because as we discussed, then the ratio of time spent on IO becomes increasingly more important. So with all the effort that the community, both the bioinformatics community and hardware community, has put into improving the performance of read mapping, it is, I think, that more important to focus on storage systems for those new systems because of the alleviated IO bottlenecks in them. I'm not sure if that addresses your question or that was the point you were referring to.
Mm-hmm. Mm-hmm. Exactly, yeah.
Cool.
Feel free to ask questions directly to Nika. It's a great opportunity. She's here. She's the first author, so she can answer your questions directly.
And also, if you have questions or something to discuss, this is my email. Also, feel free to contact me and I'd be happy to discuss further.
So for long reads, since, for example, nanopore reads, the read length is really variable. Can go anywhere between 100, let's say, or 30, all the way to 2 million. Do you see any benefits of using the exact matching filter for those short pieces, and then the rest will go through the other filter?
I think that's depends on how many of those pieces, how many of those reads, how many percent of the read data set are constituted by those short reads. However, GenStore EM, which is used for exact match filtering, currently does not support variable read length. So it is used mostly for short reads that have mostly fixed read sizes in a data set. So it requires further optimizations to be enable us to handle variable read lengths. So currently, no, but I think it's definitely something to look into and expand for variable read length.
So it's always recommended to use the other filter, regardless the sequence length, for nanopore data, right?
Yeah, exactly. Yeah. For short reads, we can use both filters, EM and M, because we would have reads that would exactly match and reads that would not. And GenStore NM has no restriction on read size. So that can be combined for short reads, but for long reads, GenStore NM would be used.
That's very good. And any restrictions on the edit distance threshold, for example, or any parameter of read mapping?
For GenStore NM?
Everything.
Yeah, sure. For EM, so we look only for exact matches currently. So that would, the design wouldn't change. But for GenStore NM, so we tune the parameter of, basically, actually, let me show you a figure here. Yeah. So we here pick some number of seeds per read to send to the host system for full read mapping. So that does not change our accuracy because there is no false positive in filtering, because if we are not filtering something inside the SSD, we just send it for full read mapping or whatever the host system does. However, the larger this number of seeds would be, we would have more reads filtered, but more work to be done inside the SSD. So there's a trade-off, basically how much work we can afford to do inside the SSD and how much read can be filtered or how much performance benefit we can get. So we found this number a reasonable number across different species, but most definitely it is possible to calibrate this based on the average read length or based on the sequencing error rate or genetic variation, or the specific given the SSD configuration, the available bandwidth inside it. That is a parameter in GenStore NM, so everything can easily change based on that one parameter. So it's in a sense a parameterized design based on N, and can be, and I think it should also benefit a lot from being calibrated from different use cases to provide the optimum performance.
I see. And still for the exact match filtering, it's not limited to any edit distance threshold, although it's require exact matching, but still the rest of the read will continue with the normal read mapping,
yeah,
right?
Exactly.
CPU side.
Yeah.
So even if they have some mismatches, they will still be detected in the next step.
Exactly. Yeah.
Okay.
And I think that it is possible also to expand the design. Maybe instead of exact matches, we use some of the other work done by some of our Safari members, so that we can detect the reads that are not exact but highly similar. So that is probably an area for it to expand.
Yeah, I like that.
Yeah.
Any more questions?
And actually, now that we talked about the area of expansions, I would like to also emphasize about GenStore that what we all co-authors envision is that to use some of our, let's say, design insights and the constraints that we had to work through as some skeleton on which more optimizations or more filters can be built based on, let's say, various use cases, genomic use cases, or even non-read mapping workloads. So we would like to, in a sense, emphasize these techniques that can be applied also in other contexts, not only read mapping.
I see.
Yeah.
Let me check on YouTube if we have more questions.
Be applied.
Right, I think we don't have any questions on YouTube. Do you want to add anything else, Nika?
No, just saying that again, thank you everyone for listening. And yeah, please contact us if you want to discuss more about this or have further questions. Yeah, we'll be happy to discuss. That's
very nice. So thank you so much, Nika, for giving us this opportunity to present on very recent work, GenStore. I'm sure the student get some or learned at least something new today. That was very nice. The slides are already uploaded to the course webpage. The video will be there. So if you missed it, you can watch it again. Thank you so much, Nika.
Yeah, thank you very much, Mohammed, and everyone.
Yeah. And we will meet next week with another topic. We will let you know, and enjoy the rest of the day. Thanks, everyone.
Thank you. Bye.
Bye-bye.